This presentation treats the Hilbert Book Model project. The target of the project is the generation of a mathematical model that can be used in order to investigate the structure of the foundation and the lower levels of the structure of physical reality. I am a retired physicist. I spent my career in high-tech industry.
This lecture introduces you to the Hilbert Book Model. The model deviates considerably from the models that constitute contemporary physics. The model is strictly based on a trustworthy foundation. The Hilbert Book Model selects Hilbert spaces for that purpose. The model applies a system of Hilbert spaces. These Hilbert spaces all apply the same underlying vector space. The Hilbert Book Model represents my personal view on the lower layers of fundamental physics. A quaternionic Hilbert space can easily be structured as a dynamic model in which all past, present, and future geometric data are stored. Therefore, the corresponding space progression model becomes paginated like a book. It consists of an ordered sequence of static submodels. That is why the project got its name Hilbert Book Model. Please look at the book or paper, The Setbacks of Theoretical Physics. This is part 2 of a multi-part presentation. This part concerns the third phase of number systems. New items are parts of change that compensate each other. Tricks that work in isotropic conditions, and new second-order partial differential equations. In the third phase of number systems, all convergent series of numbers end in a limit that is a member of that third phase. This fact enables the differentiation of the third phase. Differential calculus shows that the third phase can change. The third phase shows astonishing behavior. It has the habit to remove deformations. Without disturbing actuators, the third phase stays flat. Along a direction line, change can be described by a partial differential. If in a region of the space coverage inside this direction line all converging series of coordinate markers result in a limit that is a coordinate marker, then the partial change of the space coverage along the direction of R is defined as the limit. If the region is covered by all its irrational numbers, then this limit exists. The existence of the limit is not ensured. If the limit does not exist, then the location represents a singular point. It is also possible that the surrounding region is covered by an enclosed discrete set of point-like objects. This set is not a continuum. If the spatial part of the neighborhood is isotropic and the limit also exists in the real number space, then the total differential change df of field f equals. In this equation, the partial differentials delta f divided by delta tau, delta f divided by delta x, delta f divided by delta y, and delta f divided by delta z, behave like quaternionic differential operators. The quaternionic nabla assumes the special condition that partial differentials direct along the axis of the Cartesian coordinate system in a natural parameter space of a non-separable Hilbert space. Thus, this will be applied in the next slide by splitting both the quaternionic nabla and the function into a scalar part and a spatial part. This is not straightforward. The fact that the formula follows a kind of Cartesian coordinate system is not straightforward. The reason may be that the Cartesian coordinate systems of the number system and the primitive coordinate system of the underlying vector space are somehow coupled. In Part 3 we will see that this fact has a wider impact. The first-order partial differential equations divide the first-order change of a quaternionic field into 5 different parts that each represent a new field. We will represent the quaternionic field change operator by a quaternionic Nabla operator. This operator behaves like a quaternionic multiplier. The first-order partial differential follows from the spatial Nabla is well known as the del operator and is treated in detail in Wikipedia. The partial derivatives in the change operator only use parameters that are taken from the natural parameter space. The quaternionic del operator delivers the differential delta psi describes the change of field psi. The 5 separate terms in the first-order partial differential have separate physical meanings. All basic fields feature this decomposition. The terms may represent new fields. Phi r is a scalar field. The spatial part of phi is a spatial field. Some of the terms have special names. The gradient of fr is. The divergence of the spatial part of f is. The curl of the spatial part of f is. Also, the conjugate first-order partial differential equations divide the first-order change of a quaternionic field into 5 different parts that each represent a new field. The corresponding conjugate first-order partial differential is then. The conjugate first-order partial differential follows from. This again splits into 5 terms. All dynamic quaternionic fields obey the same first-order partial differential equations. For the conjugate quaternionic del operator holds. You can find these on Wikipedia. These formulas do not contain physical units. Do not confuse these symbols with similarly looking Maxwell equations. Maxwell equations are always presented decorated with physical units. Maxwell equations ignore the real part of the quaternionic first-order change equation. Instead, Maxwell equations consider the new freedom as a gauge. A gauge is sometimes called a renormalization. Physical units represent the adaptation of the considered subject to units that experimental physicists use to measure that subject. In fact, light speed c is such a physical unit because it represents a physical unit measured in meters per second. Physicists use permittivity epsilon equals epsilon epsilon for the electrical field. In free space epsilon equals 1. Physicists use permeability mu equals mu mu for the magnetically field. In free space mu equals 1. The two physical units are related via light speed epsilon mu c superscript 2 equals 1. These are the physical units involved with Maxwell equations. Far more physical units exist where experiments are involved. The separate operators delta r times delta r and the inner product of two spatial deltas are also Hermitian operators. The inner product of two spatial deltas is known as the Laplace operator. Here the symbol represents the spatial del operator. The two Hermitian operators can also be combined in one formula. This is the D'Alembert operator. It gives rise to the quaternionic equivalent of the wave equation. The solutions to the two homogeneous equations differ. These two equations offer different solutions. They deliver different dynamic behavior of the affected field. One of the second-order partial differential equations results from combining the two first-order partial differential equations phi equals psi and zeta equals asterisk phi. This is not the quaternionic equivalent of the wave equation. The equation has no waves as its solutions. The inhomogeneous Poisson equation that corresponds to a sudden Dirac pulse response under strict isotropic conditions runs. This solution corresponds with an ongoing source or sink that exists in the field. A point-like stationary spatial pulse cannot start a shock front. The stationary spatial point-like object must be a sink or a source. In physics, this means that stationary point-like masses do not exist in physical reality. Change can take place in one spatial dimension or combined in two or three spatial dimensions. Under the proper conditions, the dynamic pulse response of the field is a solution of a special inhomogeneous equation. Here theta, tau, is a temporal step function and delta, spatial q, is a spatial Dirac pulse response. For the spherical pulse response, the pulse must be isotropic. After the instant tau accent, the equation turns into a homogeneous equation. A remarkably simple solution is the shock front in one dimension along the line spatial q to spatial q accent. Environments that represent nearly isotropic conditions feature a striking correspondence between one-dimensional and three-dimensional representations. This becomes apparent in spherical coordinates. The second line describes the second-order change of psi r in one dimension along the radius r. A solution to this homogeneous equation is so, two solutions of one of the two the homogeneous partial differential equations are equivalent in a striking way. This is a one-dimensional solution and a three-dimensional, isotropic, solution. This equivalence introduces a mass-energy equivalence for the corresponding solutions. One of the solutions represents a primitive dark energy object. The other solution concerns an equivalent dark mass object. These are very tiny field excitations. Also, two solutions of the other of the two the homogeneous partial differential equations are equivalent in a striking way. This is the quaternionic equivalent of the wave equation. The solutions are not waves or wave packages. Since centuries, these solutions are known to mathematicians. These are also very tiny field excitations. In isolation, dark objects are very tiny field excitations. In isolation, no experiment can detect them. Only cooperating in huge quantities, the dark objects may become noticeable to experiments. Dark matter objects appear in the footprints of fermions. Dark matter objects may also appear as halo around galaxies. Dark energy objects appear as chains in photons. For enclosed regions, the continuity equations that hold inside the enclosure relate to the balance equations that consider the transfer through the boundary of the enclosure. The relation is that the quaternionic spatial del operator is replaced by a normed spatial number that represents a part of the boundary. The relation is that the quaternionic spatial del operator is replaced by a normed spatial number that represents a part of the boundary. The balance equation then takes the form This result separates into three parts. The first part concerns the gradient of the scalar part of the field. The divergence is treated in an integral balance equation that is known as the Gauss theorem. It is also known as the divergence theorem. The curl is treated in a corresponding integrated balance equation. The previous equations can be combined in the extended theorem. The trick can be used in other ways. For example, one dimension less, a similar relation leads to. This is known as the Stokes theorem. The curl can be presented as a line integral. Several tricks that work in the third phase of the quaternionic number system were discovered by mathematicians in the past centuries. Experimental scientists checked the resulting formulas with dedicated experiments. The mathematicians used quaternionic-like formulas. The experimental scientists specified their formulas using physical units. This resulted in many formulas. The third part of this multi-part presentation will be devoted to these formulas. This ends part 2 of a multi-part presentation that concerns the Hilbert Book Model. This part concerns the third phase of number systems. New items are parts of change that compensate each other. Tricks that work in isotropic conditions, and new second-order partial differential equations. Part 3 concerns the third phase of number systems. New items are formulas that became famous in literature and represent combinations of continuity equations and balance equations. Both mathematics and experiments are covered. Experiments use physical units.